Okay, so welcome to day 3 of these lectures. Uh, so to recap so far, what we've seen is there's this transformation between uh, a relaxed form of differential difference equations and sheaves on certain ruled surfaces. Now, there's still some things missing from this picture. And one of the big things is, you remember the original motivation was to understand these isomonomy deformations like Pan-Levey. And so we need to have an idea of what that looks like in this commutative setting. So, so the first question is, what are isomonomy transformations? Not just in the, before we understand the commutative relaxation of what an isomonomy transformation is, we need to understand what they are to begin with. And so, for Fuchsian equations, we understand that it's transformations that preserve the monodermy. But for other equations, for general difference equations, there's only a few cases where there's anything like a satisfying theory of monodermy. So, trying to do it just in terms of it preserves the monodermy is going to be hard. But there's another way of looking at it, which works fairly well. And so the idea is, remember in the Fuchsian case, one thing we could do is we could change some of the exponents. And because the monodermy was preserved, because we insisted the monodermy was preserved, the change of coordinates, we could basically recover a solution of one of the new equation from a solution of the old equation. And this is really the fundamental property that we want to preserve. So the idea is, so given two equations, they're related by a discrete isomonomy transform. If and only if the ratio of fundamental matrices, or sorry, if and only if we can get a fundamental matrix for the second equation by multiplying a fundamental matrix for the first by a matrix, well, by an invertible matrix with rational coefficients or rational function coefficients. But when I say rational functions, of course, if we're in a differential case and we're over some curve, I really, of course, mean a meromorphic function on that curve. Okay, so this is just sort of the abstract notion. So a fundamental matrix, of course, being one of these matrices where the columns are solutions and the determinant is invertible. Okay, now that, of course, as stated, is not an algebraic condition, but we can turn it into something algebraic. So the idea is let's just talk about the ordinary difference case to begin with. So what this is saying is that there's this rational matrix, C, say, such that multiplying our solution by C gives a solution of the new equation. So C of z plus 1, V of z plus 1 is A hat, where A hat is the new equation, times C of z, V of z. And so we can move C of z plus 1 to the other side. And thus we see, modulo some very mild assumptions about how our actual equation behaves, that, well, and in particular, if we then say that this has to happen for all solutions, we can basically play this game with the fundamental matrix. And what we see is that A hat is equal to C of z plus 1, A of z, C is z inverse. So if you like, this is a non-scalar gauge transformation. And that's what an isomonomy transformation means. It is, in the difference case, is this kind of gauge transformation. The one extra thing we say is that for a symmetric equation, C should be symmetric. And that's because, for a symmetric matrix, for a symmetric equation, what we mean by a solution is a symmetric solution. Because after all, that's what we meant by singular, was that we didn't have one. And so the fundamental matrix actually is symmetric. And so when we change from one fundamental matrix to a different fundamental matrix, we're multiplying by a symmetric function. Now, this is actually not quite the case. Because we could actually have in a case where we have equations with different symmetry. So for instance, we could go from an equation that's symmetric with respect to z goes to minus c, and gauge that to an equation that has symmetry under z goes to 1 minus z, say, or minus 1 minus z. And there actually are going to be gauge transformations that do that. I mean, the rational matrices that do that, and they're no longer symmetric, but of course they have to satisfy something like a symmetry condition relative to A in order for this to work properly. Okay, and then of course there's the differential case, which is, if we can do a similar thing here. The differential case, and then we just solve I'm sorry, there should be an A hat. And thus, putting everything together, we see that A hat is, oops, there should be a C inverse. A hat is C, A, C inverse minus, plus C prime, C inverse. And so that's what a discrete isomonomy transformation looks like in the differential case. Okay, now you can talk about continuous isomonomy transformations. Those are harder to think about algebraically, although it is possible. But definitely in the end, the theory is not going to be as satisfying for continuous isomonomy transformations. So the most that the theory, the sort of the cleanest thing the theory tells you is how many continuous isomonomy transformations you have. But it's not going to do a great job on telling you, on sort of interpreting them geometrically. Whereas we'll see a bit later that discrete isomonomy transformations, especially there are some particularly nice class of discrete isomonomy transformations, in particular ones that don't make your singularities worse, that have a very natural geometric description. We'll see that later. Okay, so that said, so the commutative relaxation is just going to be A hat is CA inverse. Because, well, okay, in the differential case, it's pretty clear because we're supposed to be sort of taking the limit in which our shift goes to 0, and so that just turns into conjugation. And here, okay, we should be rescaling the time variable, which means the derivative gets multiplied by h bar, and then h bar goes to 0. And so this derivative term goes away. So the relaxation is just a conjugation. So this would be called a discrete isospectral transformation. Okay. So the thing to note is that you can do this for any rational matrix or symmetric rational matrix if it's the symmetric case. So in particular, any matrix over the base curve of our ruled surface, you can do this for. And of course, if you do that, what's going to happen is you're going to get nasty apparent singularities most of the time. Where here apparent singularity is, of course, a slightly more subtle thing, but you're basically going to make your singularities worse. So, but we can still say somewhat about what's going on just in this generality in terms of this dictionary between Higgs type equation, Higgs relaxations, and sheaves on ruled surfaces. So remember, the general framework is we're turning our matrix A, which basically lives on, is a meromorphic matrix on pi upper star V, where pi is the map from our anticanonical curve to our base curve. You can check that that actually is the right thing, even in the differential case, that this basically is what the structure of A is. Okay. And what we're doing then is, or sorry, that A is, well, okay. And we're factoring as A as B bar inverse B, where B is now a holomorphic map from pi upper star V to pi upper star W. Okay. And the various things of, when we're looking at the difference case, we had this B0 and this B infinity. Those are basically what B looks like on the two components of Q in the ordinary difference, the non-symmetric difference cases. And similarly, the factorization coming from the differential case is basically you have one factor living on the reduced curve, and then you have the second order contribution, which is the B0 part. So this is this, and then once we have this, we turn this into rho upper star V to rho upper star W, where rho is the natural map coming from our ruled surface. And this was basically just by saying, hey, the equation of Q on the ruled surface is degree 2. And so we can write the coefficients of B in terms of the ruled surface and then get rid of any quadratic terms and get something which is basically linear relative to the fibration. Okay. So, and then of course, then we do the standard, do the adjunction to, or right, and this gives us a thing on the ruled surface, which agrees with what we would have gotten by doing the adjunction from the original argument. Okay, so this is what we're doing. So what is an isomonomy transformation doing? Well, it's replacing V by V prime via some rational map of vector bundles C. So Nilini wants me to remind you what W is. So W here is a vector bundle that lets you do the factorization. So in particular, there's always a factorization like this, over the generic fiber. And this is just Hilbert's theorem 90. Generically, V looks trivial. So A is just a matrix. It has the right symmetry. Hilbert's theorem 90 lets us factor it. And that works basically until you get to the point where you don't need to use Hilbert's theorem 90 to actually do the factorization. So you can always do this sort of factorization meromorphically. And then you can build in the poles to make it holomorphic. And then you realize that there's a minimal way of doing this. And so W is the minimal vector bundle such that you can make this factorization work. Now, what you can do algorithmically is once you have a holomorphic factorization, you take the determinant, and that's going to be some polynomial of degree n in y and appropriate degrees in x and w. Let's say we're in the P1 case. And that's going to have some factors that are independent of y, that just depend on x and w. And so that's just some homogeneous polynomial in two variables. It factors. It factors completely over the algebraic closure. So you look at those roots. And anytime you have such a factor, and of course, if you've done things right, you might not have any such factor. But if you have such a factor, you look at the I guess it's, well, either rows or columns, depending on which side you like the matrices stacked on. You look at, let's say it's rows. You look at the rows of your matrix, and you look at the homogeneous linear combinations of the rows of your matrix, and you look for ones that vanish at one of those roots, such linear combinations. If there aren't any, well, and of course, there's going to be some boring ones where it's just all the coefficients of the linear combination vanish. But there are going to be, if there are interesting ones, then it's easy to see that you can then reduce that interesting linear combination to one where at least one of the coefficients is degree 0. I mean, the point is we have this vector bundle in the picture, so our different rows are actually have different degrees. So we take homogeneous combination, we have to multiply by homogeneous matrices in homogeneous polynomials in x and w. But the point is we can always arrange for that to have a degree, one of those coefficients be degree 0, and then do homogeneous row operations to reduce to the case where we actually have a row now, which is a multiple of that appropriate linear factor of our determinant. At which point that we then divide that row. And what that's done is it's made W smaller degree. And then we keep doing that until there's no such reductions left. And that's the minimal W. Okay, so, but for a lot of this argument, whether W is minimum or not is not entirely, is important, but we can mostly let slide. So a lot of it, in particular, if I give you a sheaf, it's very common. It's generically going to be the case that it'll have a V and W that it comes from. It's less generic, although it's still reasonably generic for it to be the minimal W. Okay. So in any case, C is itself a rational map, but now, of course, on our base curve, which I'm going to take to be P1 just to make things simpler. And I should say also, there's not as much interesting stuff going on in the higher genus cases anyway. Okay, so C is this rational map, and rational maps factor. So we can factor it through another vector bundle V double prime. And of course, there's a minimal thing here. We don't have to take it to be the minimal thing if we don't want to. Here it's actually very easy to say what the minimal thing is. V and V prime are vector bundles on P1 with the same generic fiber because we have this meromorphic map between them. So in particular, they're both contained in the same vector space of meromorphic sections, basically. And so we can take their sum inside that. And that is going to be another basically lattice inside the sheaf of meromorphic sections. And that's V double prime. So here it's easy to see that there's a minimal thing. It's only when we have this extra coordinate that we have to worry about whether there's a minimal symmetric thing. But it's not too hard to see that there's also going to be a minimal. Even if we were on Q, we could do the same game and then say, okay, well, if it's not invariant under the involution, we make it a little bit bigger so that it is. Okay, so in any case, so we have this factorization of C. So to understand isomonomy transformations, it's enough to understand the case that C is actually holomorphic, or the case that the inverse is holomorphic. But if we can understand the holomorphic case well enough, then we can say, yeah, well, the inverse holomorphic case is just the inverse of that. So that's not so bad. Okay, so what do we have now? We have our matrix B. And we should be a little careful now. C is of course a function on P1. We need to turn that into something on C, on Q. So we have this partial picture here. So pi upper star V is mapping by B to pi upper star W, but we also have this map to pi upper star V star. Okay, and we want a matrix B prime that finishes this picture. Because what we can always do is we can take our sheaf or take our matrix B here, turn it into a matrix A, conjugated by C, and then turn it back into a matrix B. So there certainly is a B prime. And we can hope for us to be able to complete this picture. And indeed, the same sort of reasoning that tells us that we can always make B holomorphic before making it minimal tells us that, possibly, conceivably at the cost of B prime not being minimal, we can always finish up this picture. And get another symmetric matrix in this picture. Now, what's always going to be the case is there's always going to be a meromorphic arrow when pi upper star V, when pi upper star W prime is the minimal factorization of the gauged A. But in any case, in complete generality, we have this picture. If we just say, okay, I don't care whether the factorizations I picked were minimal or not, take any factorization for both rows, there's still always going to be, well, possibly at the cost of making W prime bigger, we can always make this factorization work. Even if the starting thing, even if the initial, sorry, I keep gesturing at my iPad and I realize you can't see me gesturing at my iPad in a useful way. But basically, even if B is not minimal, there's a least choice of W prime that makes this diagram all work. Okay, so what does this mean algebraically? Well, so of course, we can turn all of our pi upper stars into rho upper stars by the same reasoning as before. With the appropriate twisting. And it's still true that the matrix C is just the pullback of the appropriate thing. I guess if we want to be really pedantic, we should include the twist by S, but that's not actually going to change what the coefficients of the matrix look like, at least in this setting. I should note that this technical issue of twisting by S actually is important in the non-commutative setting, and it's what gives you an actual gauging type effect rather than just a conjugation. Okay, so this is what the picture looks like. And then what we're looking at is the co-kernel, or rather the two co-kernels. And so the natural question is, how are the co-kernels related? I figure how does M prime differ from M? No, and I should not have written that there. See if I can move that. Yes, I can. Good. Okay. I realized I wanted to actually write, the co-kernel of rho prime C somewhere in this picture. Okay, so standard games with short exact sequences, we get, we get an induced map, and we can also take these co-kernels. Well, this is going to be rho upper star of the co-kernel of C. Let me call that N. And N prime, except twisted by S. Right, so the point is, C is a map between vector bundles of the same rank. And we're assuming it's invertible generically, and therefore it's injective. So we have zeros coming in there. Now, I should have been careful there. So what we have is whatever this is mapping in by the snake lemma. And then we get, the co-kernel of this blue map on the other side. Okay, and this is for those of you who know commutative algebra, this is basically just the two ways of looking at the spectral sequences associated to this double complex. I mean, the two, it's just comparing the two spectral sequences for this double complex. But that's just a very fancy way of saying, yeah, we do the snake lemma calculation, everything works. Okay, so in particular, the map from M to M prime, well, firstly, there is a map from M to M prime, and the kernel and co-kernel fit into this picture. Okay, but we can say more, because V and V prime are vector bundles of the same rank. So N is torsion. And well, W prime is supposed to have the same rank as everything else. So N prime is also torsion, which means that up to some possible multiplicities, N is essentially a disjoint union of fibers. I mean, rho upper star N is basically a disjoint union of fibers, as is rho upper star N prime. And so what we see is that the kernel of the kernel and co-kernel of this map from M to M prime are supported on a finite, well, I guess set-wise supported. It's a finite set of fibers. And in particular, if M were minimal, then the kernel would have to be 0. Basically, because if you look at this picture, the kernel is contained in rho upper star of n, which is a sum of structure, which is and n is a sum of structure sheaves of, possibly non-reduced points. So basically fat points in P1. And so when we pull that back and take a subsheaf, we're going to get, structure sheaves of points again, or subsheaves of structure sheaves of fibers is the typical kind of behavior. And that just isn't going to exist in M without breaking minimality. Okay. So we basically have this nice little extra we have this feature that what's really happening then. So and also is, if M prime is also minimal, then the co-kernel is 0-dimensional because it's supported on fibers, but M prime shouldn't have any maps to actual line bundles on fibers. And so what we see is that the typical behavior is that we have a short exact sequence where Z is a sheaf with 0-dimensional support. So we get M goes to M prime goes to Z goes to 0. So this gives rise to a couple of natural things. This tells us there's actually a couple of natural things we can do. So 2 natural cases. So one of them is, fix a point. And well, okay, let's just for the moment say X and X, although it works a lot better if X is in Q. And then we can have a canonical exact sequence which is basically and now I have to remember whether it's yes. There's covariant or contravariant in the extension. So in other words, this is the universal extension. So M prime is the universal extension of this point sheaf by M. Okay. And then the other case is basically the inverse. Where now instead of taking the universal extension, we take the universal map from M to this point sheaf, and then take the kernel of that. So these are sort of the 2 natural types of isomonomy transformations were led to by this observation that isomonomy transformations are changing our sheaf by something 0-dimensional. Okay. So right? And so we'll see later, this is, well, so this is most natural, well, right. In the non-commutative setting, there are very few points, because the only points are points of this anticanonical curve. And so if we want to get something that's actually going to extend to actual equations, not just the Hitchin case, we should take this point to be a point of Q. Okay. Now I should also say that this is not the only thing you can do, although in the most generic cases, the only thing you can do. But depending on what your singularities look like, it turns out, sometimes there are going to be natural subspaces of either this X group or the Hom space. And so you can take those subspaces rather than the full thing and get something which is still natural from the equation, but not one of these two operations. Okay. Right. So one thing to note, that if X is in Q, well, in order to have a map like this, or in order to have an extension, X and the support of M cannot be disjoint. So in particular, X has to be contained in the support of M, but X is in Q. So X has to be contained in the support of M intersect Q. In other words, X basically has to be a singular point. So this is an important fact here, is that in general, the nice isomonomy transformations are by singular points of your equation. Okay. I guess another thing I wanted to say, well, yeah. So the other thing we should note is that, these really do correspond to isomonomy transformations, and that's because anything like this is going to give rise to an isomonomy transformation using this by just following the dictionary back. Let me have a brief digression about sort of the sort of underlying reason why the translation from the co-kernel to the matrix always works. And this is actually something about sheaves on P1, and which works because we're in a ruled surface. A ruled surface you can think of as a family of P1s, and so a sheaf on a ruled surface is a family of sheaves on P1. Okay, so given a sheaf M on P1, there is a natural 5-term exact sequence in which the first two terms are powers of big O of 1 and in the structure sheaf, and then we have M, and then we have a different power of O of -1 and a power of structure sheaf. So for any sheaf, you can do this. And the proof is actually very easy. And there are even easier proofs that don't involve this, but basically we just write M as a sum of a torsion sheaf and a collection of line bundles. And then note, well, firstly, if M is globally generated, or sorry, that's not quite right. If although well, it's equivalent once you've done this factorization. But if m of minus 1 is acyclic, then we get a short exact sequence. And the thing is, we can just do this for each, for a torsion sheaf and for an acyclic line model. And those are the only two cases we need to check. And then if M is reflexive, and the dual twisted by minus 1 is acyclic, we can dualize. And thus we get a 3-term exact sequence starting with M, and then we just take the direct sum. So that tells us that there is such a thing. And then for naturality, we just need to note that this gives a distinguished triangle. Sorry, I'm digressing into derived categories. So we have a 2-term complex of tensored with O of minus 1, a 2-term complex of vector spaces, a 2-term complex tensored with the structure sheaf going to M. Oh, and let me put the the shift of M in there. So this is what we get. And then we just need to observe that, basically the same argument we did before, that W is the basically derived global sections of M, and V is up to a shift and a doing things right to get the canonicality. V is this. And so with this, so in other words, if you look at this 5-term exact sequence, each of these terms, the vector bundles implicitly arriving in each of these terms is a cohomology sheaf of either M or M twisted by minus 1. And so that basically so that makes everything natural. Okay, and then we get a similar thing for M on a ruled surface. We get an analogous 5-term sequence. Okay, and therefore, if you're given a short exact sequence of sheaves on a ruled surface, since everything was natural and we were working in the derived category, these 5-term sequences are related in a natural way, and so you get useful information out of that. And in particular, what you find is that indeed, when you do this sort of transformation to M, if you extend by a torsion sheaf, or take the kernel of a map to a torsion of a surjection to a torsion sheaf, zero-dimensional sheaf, what you end up doing is just changing V and W by points. Okay, so that's at least a start on what isomonomy transformations are, or really isospectral, because we've relaxed. So far so good. But there's another thing we kind of need to deal with is, the other thing, the reason why we were trying to move to sheaves is we wanted to understand the moduli spaces. And so the good thing is that the moduli space of sheaves is well understood. How to construct that, how to prove it's projective when it is, things like that. However, we're not actually interested in the moduli space of sheaves. We're interested in the moduli space of sheaves with a specified restriction to this anticanonical curve. And although there's some limited results along those lines, they're only for torsion-free sheaves. And since we actually care about one-dimensional sheaves, which are always torsion, so it's not quite good enough. So we need to do something to get around that. So the problem, how do we take into account the restriction of M to Q when constructing moduli spaces? Okay, so and we've actually seen a little bit of hint as to how we can make this work. So remember when we were talking about, when we were using this section, we were sort of saying, yeah, okay, well, it corresponds to an equation. But then we said, okay, but it had some singularities. You know, a rank 1 equation, but it had some singularities. And we would basically, but we started doing some minor birational transformations, these elementary transformations where we blow up a point and blow down to the fiber it contains. And we could resolve those singularities by doing so. Now, in general, we can't expect to just stay on a ruled surface and get rid of all the singularities, but we can still hope to separate the curve, the spectral curve, from the anticanonical curve. And so the idea is, if M meets Q, we blow up a point of intersection. Okay. And there are two cases. Well, so let me first say, so let's pi, from x tilde to x be the blow up. So the first thing we note is that there's a new anticanonical curve. There's a new anticanonical curve. And what it looks like is you take the pre-image of Q, and then you remove one copy of the exceptional curve of the blow up. And this is just, well, okay, this isn't Hartshorne. So this is how the anticanonical curve is related. And this just follows directly from the formula Hartshorne gives you for how the canonical class is related to of a blow up is related to the canonical class downstairs. Okay, so this is what the new anticanonical curve looks like. And the point being that, and in the end, this is why we need to always blow up points of Q to retain nice Poisson structures, because this formula works at the level of divisor classes always. But if the point we blew up was not on Q, pi upper star Q is not going to contain the exceptional curve, and so this will no longer be effective. But because we're always blowing up a point of Q, this is going to be an effective divisor and will be the new anticanonical curve. Okay, what about M? How do we get it? How do we lift M? Well, it turns out there's a minimal lift of M tilde, of M, which for various reasons I call pi star shriek, pi upper star shriek of M. Yeah. Which has two properties. The first is that its direct image is M, and it's acyclic for the direct image. So it has no higher direct images, and the actual direct image is M. And any other sheaf with this direct image, including acyclicity, has this minimal lift as a subquotient. Now, the formal construction of this gets into duality theory, and so it's a little requires a bit more prereqs. But the simplest way of describing it, that's not as clear that it actually behaves as well as you'd like, but it basically has the property. Well, so the first thing to note is that the actual pullback of a sheaf has direct image that sheaf and is acyclic. So, and not only is it a subquotient in that case, it's actually a quotient. And so we get a short exact sequence like this with n maximal. So basically, we take the actual pullback, and then we mod out by as many copies of O of O of minus one on the exceptional curve as we can, and that gives us pi upper shriek of m. And the point, and the reason why O of minus one on E is the right thing is because O of minus one has no cohomology. It has no direct, it has no global sections, it has no higher cohomology. And so when we take the long exact sequence of pi lower star, coming from pi, applying pi lower star, this just completely goes away, and we get an isomorphism between those two, between the direct images of these two. So this is sort of one way of thinking about the this minimal lift. So the fancy version is that this fact that the direct image of pi upper star of m is m translates after doing some injunctions to saying that there's a map from pi upper star of m to pi upper shriek of m, and we take the image of this. But this requires understanding pi upper shriek, understanding why pi upper shriek happens to be an actual functor, etc. So there are details in the Poisson moduli space paper. Okay, so this gives us a way of lifting m. And the key point is this short exact sequence. So what we see is that the support of m, well, so downstairs, the number of intersections between m and q is the intersection number between the support of m and q. So this is the number of intersections. And then we look at what happens upstairs. And so we see that the minimal lift has class, the pullback of the class of m minus n copies of E. And then of course we get pi upper star q minus one copy of E. And right. And so then we sort of take into account intersections. And the key point is that so if Wait a second. Ah, right. So okay, I'm blanking on the argument, but the key point is that this ends up being less than C1 of M dot Q. So, and this is, I mean, the way to look at this is, you know, at least in the generic case, we have one curve, which is Q, and another curve, which is the support of M. And we're blowing up a point where they intersect. And so when we first do the blow up, both the support of M and Q pick up a bunch of factors of E in general, but we lose some of those from the support of M, and we lose one of them from Q. And so, and in bigger, if we blow up a smooth point of Q, we no longer see E in there at all. And you just check that always is going to reduce your intersection number by N. Okay. And the other thing to observe is that, you know, N is always going to be positive in this case. Because well, N is at least 1, and at most the multiplicity of the support of M at the point being blown up. More precisely, over a formal neighborhood, so on a formal neighborhood of that point, M is a direct sum of sheaves, and N is the number of summands. Okay. Now, so we see that if Q is smooth at X, the intersection number goes down. And M still meets Q transversely. That is, there's no component in common. So we can iterate. If Q is not smooth, so if Q is singular at X, then we may have a problem. Because the problem is when we blow up a point of Q, the multiplicity of the exceptional curve in the blow up is the multiplicity, in the pre-image at least, is the multiplicity of the point being blown up. Now we're then subtracting 1, but if it's singular, the multiplicity is bigger than 1, and so we still end up with a multiplicity. And so the problem is going to come when M itself contains that, the minimal lift of M still has some copies of the exceptional curve in it. because that is, then they're going to have a component in common, and we're never going to be able to resolve that. Okay. However, if we remove copies of E from M, or more precisely, we take the natural map base like this, or take the torsion-free quotient. By basically, by modifying M slightly along E, we can remove some of those copies of E and get something, get M, which is closer to being transverse, and eventually we can make it transverse. Okay, and the direct image will differ from M, or from the original M. Sorry, this should be pi upper star, pi star speak. Anyway, will differ from the original sheaf by a zero-dimensional sheaf. And so the second case can always be resolved always be fixed by an isomonomy transformation. And moreover, it's a canonical isomonomy transformation. And moreover, this canonical isomonomy transformation makes the singularities simpler. So essentially what this is saying because after all, it's making the singular, it's getting rid of this obstruction to separating this, which means basically that our singularities are, they're resolvable. So in some sense, at least, they're simpler. And therefore, we can think of this as a flavor of apparent singularity. So in general, so modulo this issue, we can reduce to the case that our sheaf is disjoint from Q at the cost of changing the surface. Okay, so this is and the benefit of this, the big benefit, well, is twofold. Firstly, for M to be disjoint from Q, is an open condition, in flat families of sheaves. So these are classified by an open subset of the usual moduli space. So in other words, from the standard theory of moduli spaces of sheaves on surfaces, there is a projective scheme that classifies sheaves with specified, let's say, Hilbert polynomial, modulo some choice of ample line bundle. So there's a projective space that classifies sheaves with given Hilbert polynomial, modulo subtechnical conditions, which we'll talk about later. But then once we have this projective space classifying, projective scheme classifying sheaves, the sheaves that are disjoint from Q are going to be an open subspace, an open subscheme. So in other words, once we've separated ourselves from Q, we can just look to the literature to say that yes, there's a moduli space. There's a nice algebraic moduli space. So the construction of the moduli space becomes easy in the sense we can look it up. It's of course very hard to actually, I mean, it's, takes quite a bit to actually do the construction, but somebody's already done the work for us, so that's good. Now, there's another thing we get, which is that there's a formula for the dimension coming from this. And that's because, given numerical invariance. Now, when I say there's a formula for the dimension, of course, we should be careful. It's really a formula for the expected dimension. And then we have to be a little careful about when the expected dimension is actually the right thing. But the point is, we know what infinitesimal deformations of sheaves look like. I mean, now that we've reduced this to the standard theory, we know what the infinitesimal deformations look like. And so we know what in other words, we know what the tangent space looks like. And so the tangent space is an X group. And the usual game when you say, oh, okay, I'm interested in a particular cohomology group, is the first approximation you should take is always the Euler characteristic. And here we have a very nice fact. So this is, the dimension of the Hom space minus the dimension of the X plus the dimension of X2. But we have Serre duality. So the dimension of X2 is the dimension of the Hom from M to M tensored with a canonical class. But we understand the canonical class because we have this nice anti-canonical curve. And so we can rewrite this, since we don't care about having a natural isomorphism, we just care about the dimension, we can rewrite this in terms of the anti-canonical curve. Okay. But M is disjoint from the anti-canonical curve. So this is just Hom MM. And so we see that the dimension of the tangent space, at least, and then we have to worry about whether things are smooth. So the dimension of the tangent space is twice the dimension of the endomorphism ring minus the Euler characteristic. Actually, this is the definition of the Euler characteristic for M. This is something called the Mukai pairing in general. Okay. Now, the moduli space theory only really works when the endomorphism ring of M is basically when M has no non-trivial endomorphisms. And if you think about it, that's not a massive constraint to be putting on, because if M has a non-trivial endomorphism, Schur's lemma tells us that we can split off subsheaves in a natural way, and we get some natural splittings of M, or at least a natural filtration of M. And in particular, M is going to be is going to correspond to something like a reducible equation. And so it's going to be built up out of simpler equations, and we can feel free to mostly ignore those sorts of cases. So this is not a massive thing. Sorry, this should be the dimension, of course. And so this is really just 2 minus chi mm. And chi mm, it turns out, can be computed using intersection theory. And it's just the self-intersection. Sorry, minus the self-intersection. Yeah. And so we see in general that the dimension of the tangent space, so this is Hertzebruck, Riemann-Roch. For surfaces, with some help from the fact that our surface doesn't have, well, assuming we're on a rational surface at least, because a lot of the terms are simpler in that case. The structure sheaf of X, for instance, has Euler characteristic 1 because it has no higher cohomology. So the dimension of the tangent space is 2 plus the self-intersection of M. Okay. So in particular, the tangent space, the dimension of the tangent space, let me just call it dimensions in quotes, is 0 if and only if the support of M has self-intersection -2. Okay, and now we use, again, Hertzberg-Riemann-Roch to tell us that since M dot Q is also 0, by assumption, we're disjoint, this implies M, right, and when I say M here, of course, you should be talking about the support of M as a scheme, in the Chern class sense. This implies that M is a -2 curve. That is a rational, it's a smooth, it's supported on a smooth rational curve of self-intersection -2. In other words, rigid equations roughly corresponds to -2 curves. I mean, this is modulo checking that the actual, expected dimension is correct, but this is what we get. The other thing we note we understand the lattice of divisor classes on X well enough to conclude, well, in fact, actually, let me not say this. This is actually more general fact. Oops. More generally, there's a formula for the arithmetic genus of the support of M, which, because it's disjoint from Q, simplifies. And it's 1 plus the self-intersection over 2. And therefore, in particular, M squared is even. And, well, the dimension is 2 plus, sorry, is twice the genus. And therefore, the dimension is even. So, this is something that we need to explain. Why are we always getting something even dimensional? And we have the following theorem. The moduli space of sheaves on X has a natural Poisson structure. So X here is a Poisson surface, Poisson projective surface. So given a Poisson structure on X, the moduli space of sheaves has a natural Poisson, has an induced Poisson structure. Moreover, so one thing that happens in differential, so there's, you can talk about Poisson structures in differential geometry. I mean, that's where they came from originally. And one thing you get from a Poisson structure is, it's giving you this alternating pairing on the cotangent sheaf. And in particular, what that means is that at any given point, there's a natural subspace of the tangent space, which is basically the, and which is annihilated by the radical of that natural pairing, of that pairing given by the Poisson structure. And you can start at any point, and basically you get this space of flows, and because everything is alternating, it's an even dimensional space of flows. And you can just sort of integrate that out. And that gives you a submanifold, which is called a symplectic leaf. And they're always even dimensional. And the reason they're called symplectic leaves is because there's an induced closed 2 form on that, a non-degenerate closed 2 form on that submanifold. But you can do that for any point. And of course, if you start with the point that's not in the symplectic leaf containing, if you start with one point, get a symplectic leaf, and then take a point that's not in that symplectic leaf, that symplectic leaf is going to be disjoint, because when you integrate out, you can never intersect, because this is an invertible process. And so you actually get a foliation by symplectic leaves. Now, one thing you lose in the algebraic setting is it's almost never the case. If I just hand you a Poisson structure on an algebraic variety or an algebraic scheme, it's almost never the case that the symplectic leaf foliation is itself algebraic. However, in this case, you're good. So in particular, these symplectic leaves are themselves algebraic and are the fibers of, well, to make this work everywhere, it's not quite the fibers of restriction to Q, it's the fibers of derived restriction to Q, but that almost never matters. In other words, and also they're smooth. In other words, the moduli space of equations with specified singularities is smooth and symplectic. Now there's a massive caveat. What one means by the moduli space is not the usual moduli space. Basically, so the issue is, so remember I alluded to earlier, this theory for constructing moduli spaces has this annoying thing where it's sort of never giving you the natural equivalence relation of, yes, to, if each sheaf corresponds to a point, and isomorphic sheaves correspond to the same point, and if two sheaves correspond to the same point, they're isomorphic. That always breaks for the usual, almost always breaks for the usual moduli space. However, if you impose this condition I mentioned earlier that says that the endomorphism ring is there are no non-trivial endomorphisms, so it's just the multiples of the identity, then you actually do get something that represents the natural equivalence relation. The cost is it's not a scheme anymore, and it's definitely not projective, but it's not even a scheme. So you get something called an algebraic space, which roughly speaking is constructed in roughly the same kind of way you construct schemes, except you replace open subsets with étale maps, which is a weird thing, but this is something that gets done all the time in more advanced algebraic geometry. And so it's not a scheme anymore, but Poisson structures still make sense because if we're given an étale map of algebras, then any Poisson structure on B induces one on A. Or in scheme theoretic terms, étale map, you can always pull back a Poisson structure through an étale map. And the reason is because the sheaf of differentials isn't changed by an étale map. And we have this description where it's just, it's a bivector, it's a alternating biderivation. So it's something we can just define in terms of the sheaf of differentials. And so étale maps, and similarly, the Jacobi identity was just in terms of, the exterior cube of the sheaf of differentials. Étale maps pull back Poisson structures. And so this algebraic space thing, even though it's not a scheme, it sort of has an étale cover by a scheme, at least locally. And so you can define a Poisson structure on it by defining a Poisson structure on these schemes that cover it. And then there's some extra consistency conditions one needs to check to make that work, but everything works. This theorem is basically the main theorem of the Poisson moduli space paper, oddly enough. So this theorem is, well, a somewhat weaker version of the theorem. Was proved by Hitchin for vector bundles, or sorry, for torsion-free sheaves. No, sorry, for vector bundles. And Hurtubise and Markman for more general sheaves. The weaker version is because the full generality of looking at algebraic spaces and the full generality of looking at the derived restriction to Q are not present in those references. But if you sort of trace through what they're doing and are reasonably careful, you can carry it all through in the algebraic space setting. And in fact, actually, with a little bit more work, you can make everything work in finite characteristic. Poisson structures are less useful in finite characteristic, but the one fact that's still nice, that's particularly nice here, is the fact that the symplectic leaves are smooth, and this can be made to work in finite characteristic. Okay. So in particular, we see that in our disjoint case, okay, well that is a special case of things with specified restriction to Q. So in the disjoint case, the expected dimension is correct. Okay, and I guess I'm about at 5:30, so this seems like a good place to stop. But this does explain evenness, because symplectic varieties are always even dimensional. So this is, and there are other ways of getting at the Poisson structure for difference equations, and or rather, there's other ways of defining an alternating biderivation for equations, and it's generally easy to prove that it's an alternating biderivation, and easy to understand what these symplectic leaves look like, except I was never able to prove the Jacobi identity in any of those cases. So this is actually a very, very subtle thing. And one of the hard things in the non-commutative setting is proving that this theorem carries over and actually still works for equations. So let me stop here and throw the floor open to questions. Well, so there were two parts. The first part was explaining what isomonomy transformations look like. Okay. So basically, in terms of sheaves, what they are in terms of equations is basically a gauge transformation. And in terms of sheaves, what they are is they're either modifying your sheaf by something zero-dimensional. So either extending by something zero-dimensional, or taking the kernel of a map to something zero-dimensional, or some combination thereof.
Okay, nice.
Okay. And then, so that was sort of the first part. And then the other part was basically saying, okay, how do we actually deal with the singularities? How do we construct the moduli spaces with specified singularities, given that this is a harder problem than just constructing moduli spaces of sheaves? And the way one does that is by basically blowing up the points of intersection, arguing that the annoying cases where you end up both your sheaf and both the lift of your sheaf and the anticanonical curve contain this exceptional curve, argue that you can always sort of fix those by a canonical isomonomy transformation that makes things simpler. So it's basically an apparent singularity. And then eventually you get to the case where you're disjoint. And then the rest of it is basically just arguing why, sort of saying what happens when you're in the disjoint case.
In that blowing up process, you have interpreted your modular problem as a usual how to say, no modular problem, but
right. So once you've made a disjoint, then it's just an open subspace of a standard moduli space.
how do you check? Is it open?
Well, so the simplest way of seeing that is if you take your sheaf, there's a natural way of constructing a scheme corresponding to its support called the fitting scheme. And so you look at the equation of that fitting scheme, and you're asking for that equation for that curve to be disjoint from Q. So in other words, you're asking for the ideal containing both of those to basically to contain one. But right. But the other thing is we have the. I mean, if M is coming from this construction, it's coming from a map, pi upper star v to pi upper star. I mean, rho upper star v to rho upper star w. That's then it's getting lifted, but it still basically has some presentation. And you just restrict that presentation to Q. And then you're asking for that complex on Q to have no cohomology. But that's by semi-continuity, that's open. Because you're asking for all of the cohomology spaces to have zero dimension. So you're putting a lower bound and it's upper semi-continuous. So that's why for the completely general thing of you have any sheaf on the surface, you want to know why it's disjoint from Q. Well, that's because there's a corresponding complex on Q that's supposed to be trivial, and complexes being acyclic. If you have a complex of, well, if you have a perfect complex on a projective scheme, asking for that to be acyclic is an open condition. Yeah. I mean, so when you're talking, so what we blow up till you're disjoint, and then the deformations that preserve disjointness are the same as deformations because it's an open thing, so you get the same deformation theory. I mean, there is actually a way. I mean, you can actually compute the deformation theory, even if it's not disjoint. You can compute the deformations that preserve the intersection, but it's more complicated. Right. So the part I didn't explain, but if you sort of trace through what you're doing when you do these blowups, will follow. Is that if you take a sheaf disjoint from Q, and then on this blown up surface, and then take the direct image down to the original ruled surface, the way that sheaf intersects the Q downstairs is independent is not quite independent of the sheaf upstairs, but only depends on its numerical Chern class.
Okay.
In particular, it's deformation invariant.
I see.
I mean, we'll be talking more about this later, because one of the things we're going to want to understand is what if I can do a surface and a class of sheaves disjoint from the anticanonical curve on that surface, we all understand what the singularities of the corresponding equation look like. So if you take that thing, take its direct image down, turn it into an equation, what do those singularities look like? And so we will eventually need to understand this question of what does the intersection look like as basically as part of that. Right. So basically this process, well, the thing is, of course, we're changing the surface, which has sort of nothing to do with the specific equation. I mean, but what we're doing is we're starting with this ruled surface, which is just sort of this universal ruled surface that every equation, has an interpretation on, modular this choice of Poisson structure. But then what we're doing is we're blowing up singular points.
Yes.
So what we're doing is we're taking these continuous degrees of freedom, which is what are our singular points, and we're encoding that into the surface. So basically, so the blown up surface actually tells you, in a sense, all of the continuous data of your problem, or at least almost all of the continuous data of your problem. And then what's left over is basically, just these numerical invariant of your sheaf. And what that basically corresponds to is, your surface it's essentially corresponding to a certain collection of irreducible singularities. And the numerical Turing class is telling you the multiplicities with which each of those irreducible singularities appears in your equation. And it's also, of course, telling you the rank of the equation. But so that's basically how this. So you're not doing anything to the equation.
I see.
What you're changing is the sheaf corresponding that is coded to the equation.
I see. So
But yeah,
if you want to interpret a sheaf on the space after blowing up the differential equation, you have to blow down. Is it?
you have to. Yeah, you have to map all the way down to a ruled surface.
I see. Okay.
But one thing to note, and we'll talk more about this later. The blown up surface will typically have multiple maps to multiple morphisms to ruled surfaces.
Yeah.
And so it will have multiple interpretations.
Yes.
So a sheaf on that blown up surface has multiple interpretations. And this is even true in the non-commutative case. So you really need, you need at the very least a choice of ruling on this blown up surface to get an interpretation. And even that's sort of only true up to a scalar gauge. I mean, it only gives you an interpretation up to these scalar gauge transformations. But yeah, we'll see, for instance, that there's actually this big Coxeter group acting on this picture. This big, typically infinite group acting on the different interpretations. Right. I mean, in general, okay, on the original ruled surface, if the support of M contains a component of Q, you can't possibly separate them. But you also can't possibly interpret it as an equation. So, I mean, this shows up at, if you're trying to compactify your moduli space, this is going to show up. But those points those sheaves do not correspond to equations. They can't. However, but what happens then when you start blowing up points is you lift M in this minimal way, and you lift Q, but they can interact. And so basically, I mean, it's actually always the case that the intersection number goes down. The problem is there might be a component in common, because they started out just meeting in points, but you blew up one of those points, and so if both curves are singular, there might be a component in common. Now, there's a hope of being disjoint because we're removing one copy of E from Q and one copy per branch from M, basically, essentially, or at least assuming the sheaf splits splits as far as it can. We're removing enough copies from the support of M that we're still good. But if your singularities are slightly more complicated than that, you may not be able to remove, or you may have to do an isomonomy transformation to get rid of that, to actually fully separate them. But the point is, you're only ever doing things. I mean, as long as you are able to get started at all, you're only doing these modifications by the exceptional curve. And so, if you modify it by some number of copies of by what's going on in the exceptional curve, and then take the direct image back down, you're just changing M by a bunch of points. And so that's an isomonomy transformation. And moreover, you can do so in a canonical way, because you just take the maximal subsheaf of M that such that the support does not contain E. And that's a canonical thing, which will be isomonomy equivalent to M. So you just basically keep doing, so you do that, and then that's going to reduce the intersection, and then you keep blowing up. There's some technical details in showing that when you do that process, you do eventually get something you can separate, because you have to be a little careful about why you really do decrease the intersection number, because you removed a bunch of copies of E, which were giving you a bunch of negative, which was giving you something negative in the intersection number, and so you do need to be a little more careful about that, why you can still separate. But it does, in fact, work. So yeah, this is getting into some more technical things, but basically, one of the things you could do when you with a complex of sheaves is you can take its determinant, which is basically the alternating product of the determinants of the terms in the complex. So in particular, you can start with a sheaf on the surface, restrict it to Q, and then take the determinant. And that will always be a line bundle. Okay. And if you do this to a flat family of sheaves, you'll get a flat family of line bundles. Okay. So you have the sheaf M, which is disjoint from Q. And you're deforming this in a family, which is disjoint from Q. Well, when you restrict M to Q, you get the trivial complex, which has trivial determinant. And so every fiber, even at the boundary, the determinant of restriction to Q is always going to be trivial in this family. Because it's a flat family and it's generically trivial. Okay. But now think about what happens if M actually just contains an isolated point of Q. Well, the determinant of a point is the line bundle with that divisor. So what you find basically is that, if it intersects in something zero dimensional, the determinant is going to the determinant would have degree that intersection. So that's bad. So that tells you that there has to be a component in common at the very least. But then you basically keep arguing about what happens when you then basically keep looking and you find other components that have where the restriction is forced to be positive degree, again contradicting this flatness. And you just basically keep throwing in components that are forced in because keep adding more components because you're forced to have a component in common. Keep having a component in common beyond what you already had, and then you eventually find that you're left with Q. You eventually end up with Q once you've added in all those components. This takes some argument, but so the upshot is that indeed in this family we're generically disjoint from Q. Any fiber where you're not disjoint from Q, the support actually contains Q.